This slide introduces the heart of the furnace design, the hearth. It's the zone where the molten iron and slag collect, directly beyond the tier level. A wrong hearth diameter leads to a irregular taffel flow, low productivity, and accelerated refractory wear. The tier zone above must feed the hearth uniformly to ensure a stable tapping and consistent metal flow. Remember, the hearth is not just a container, it's the foundation of the furnace capacity and longevity. So, coming to our uh, roadmap forward, which is based on the linking production productivity and uh, hearth. So here we connect daily production, productivity and hearth load. For example, a target of 8,000 ton per day with a productivity between 2 to 2.8 gives us a melting rate of 30 to 50 ton per meter square per day. So a lower melting rate around 30 means a wider hearth for a same production, while a higher melting rate allows a narrower hearth. So higher the productivity demand, higher the melting rate, which directly influence the hearth diameter. This relationship define the balance between the capacity, the heat load, and the refractory life. So coming to a step by step, the hearth diameter calculation. So now we move to the calculation process. Step one, as you can see, that define we have to define the target production. Here the 7,500 ton per day. Step two, choose the desired melting rate, that is 40 ton per meter square per day, typical for the high productivity furnace. Step three, calculated the hearth area. So this is what it being done, and step four is find the diameter from the area. So if we round up the standard size, then it's coming around 15 meter. And always note the wording: do not exceed 50 ton per meter square per day, or you risk hearth erosion and excessive gas. So here we have a comparison of the two furnace, which can gives us a good understanding about the information. So this slide compares the two design philosophy. Furnace A is conservative design, TPD 6000, melting rate 32, area 187, and dia 15.5. So pros: lower gas velocity, less dust carryover. Cons is higher refractory cost, larger shell. Coming to the furnace B, aggressive design. That is TPD is 6000, melting 48, area 125, dia 12. Process: lower capital cost, higher hearth wear, demands higher quality coke and oxygen enrichment. For productivity above 2.5, use melting rate more than 40 to keep hearth practical. Balance cost and durability. So coming to the final design check, as you can see, that before finalizing, verify these parameters. First, the ratio of the hard dia to working volume, typically zero point 0.3 to zero point 0.4 for large furnace, that is more than 2000 meter cube. Second, taphole flow velocity should be around 2.5 to 4.0 ton per minute per taphole. For two taphole, larger diameter need more or bigger taphole. Third, hard diameter versus number of tiers. A rule of thumb, that is 0.45 to 0.55 meter per tier. Use the formula that what it's very clearly shown in the slide, and one example is also given. So these checks ensure the hearth support a stable tapping, balanced gas flow, and long campaign life.